Okay, this video is about keypad and LCD. Typically what you find there are two types of keypads, a matrix keypad and a non-matrix keypad, and these are easy to distinguish when you first pick up a keypad if you go to one of these electronic surplus stores. Let's first of all look at a matrix type keypad, and what you're going to find is you're going to have a series of keys. Now this is a standard hex keypad layout. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Pretty standard. Now, the real difference between matrix, which this is that for matrix you've got one pin for every row, and that row 1 is keys 0, 1, 2, 3. Row 2 is keys 4, 5, 6, 7. And row 3 is keys 8, 9, A, B. And row 4 is C, D, E, F. Column 1 is really keys 0, 4, 8, C. Column 2 is 1, 5, 9, D, and so on. So what you're going to find for a matrix is that there's a row pin for every row, a column pin for every column, and there's 4 rows, 4 columns, a total of 4 rows, 4 columns, 8 pins. Plus, you might actually get a ground pin as well. So 8 or 9 pins for a hex keypad, that's definitely matrix. Now it said up at the top, if you read this, that the difference between a matrix and a non-matrix has a pin for every key. So you'd have minimum 16 pins plus possibly a ground pin, 16 or 17 pins for a hex. That's a non-matrix. If you have 8 or 9, that's a matrix. That's how you determine it very easily. Now one other thing that you would want to do is figure out which pin of these 8 or 9 pins are my row 1, row 2, row 3, row 4 pins, and column 1 through 4, plus possibly that ground pin. Now the simple way to do this, if you take a look at it, with all the push buttons up, the rows and columns are not connected. Now if I happen to press the 6 key here and hold it down, that means that row 2 is connected to column 3, and there's a physical connection there. So this pin here would be connected to this pin if I hold down 6. In fact, any key that you press down is going to connect one unique row with one unique column. So if I press a 0, row 1, column 1. If I press the E key, that's row 4, column 3. If I press the 9 key, that's row 3, column 2. So the concept is, if you want to figure out the pinouts, is to have your partner push down the 0 key while you're holding it down, have a ohm meter and connect it to row 1, column 1, row 2, column 2, and so on. And basically what you're going to do is try and figure out which 2 pins, there should be at most 2, maybe 3 if there's a ground, but at minimum 2 pins connected out of the 8 pins if you have an 8-pin keypad, as we do in our lab, but it's a little different layout. But if you do this, what you should be able to do is come up with a chart like this. Now what this is really saying is that these are the pins. When I hold down the 0, these 2 pins are connected. When I hold down the 1, these 2 pins are connected. When I hold down the 2, these 2 pins are connected, and so on. So you can come up with a chart, and this is saying this is row 1, column 1, because that's where the 0 is. Row 1, column 2, that's where the 1 is. So if we go back again and take another quick look at this, row 1 is 0, 1, 2, 3. So let's go back here. And if we take a look, 0, 1, 2, 3, that's row 1. Row 2 is 4, 5, 6, 7. 8, 9, AB is row 3, and so on. So if you take a look here, all of these have row 1 common. And the only thing that's common here is, strangely enough, pin 9. So right away we know that pin 9 here is our row 1 pin. I think you can see, if you do the same sort of analysis here, that row 2, row 2, row 2, row 2, the only common pin is this one. And that's fairly easy to see. So this is my row 1, row 2, row 3, row 4. Now the column pins, let's take a look. There is column 1, column 1, column 1. And where's the ones that have column 1? That's pin 5 is column 1. If we take a look at column 2, there's column 2, column 2. If we go over across here, this one happens to be our column 2 pin. So it's very easy to figure this out. Now notice we have one pin here with no X's, because that means there's maybe 9 pins on here, but the ground isn't connected. If the ground was connected, instead of just having 2 pins connected, you'd have 3. And you have all X's all the way down here would indicate that this would indeed be a ground pin. but it's very easy to figure out what your pin layout's going to be. Now when you look at standard hex keypad encoders, if you happen to hold this key down, which connects this column to this row 1 to column 1, what you're going to find is it's going to generate a 4-bit pattern of 0. This particular key, when you press it down, is going to generate a pattern for a 5. This one's going to generate a pattern for an A. Now this is pretty much standard for the row 1 through row 4, column 1 through column 4, for any kind of keypad that has actually 16 buttons. Now it doesn't necessarily mean that you have to have a 0 here. It could be any character here, but that key, whatever it is, could be any character you want to come up with on a keypad. That's going to generate a pattern for a 0. Whatever one you happen to have here will be a pattern for a 5. This one, whatever the key happens to be, a pattern for a 9, pattern for an E, which is 1110, and so on. So if we take a look at a non-standard hex keypad, the one we have in our lab, this is going to generate a pattern for a 0 on most encoders. This is going to generate a pattern for a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, an A, a B here, a C, a D, an E, and finally an F. So no matter what characters you happen to have on, this is always going to be 0, 1, 2, 3, 4, 5, 6 is a standard kind of keypad layout. Now the next thing you have to ask yourself, well, how do we make circuitry that's going to allow us to figure out which key has been pressed? Now typically what you're going to find is that if all keys are not pressed, there's no connection between any row and column. Now one of the standard ways to do is something called Keypad Scanning, where you connect your rows all to through pull-up resistors, in our case to 3.3 volts. And if there's no key pressed on any of these things, then you're going to have 3.3 volts here, 3.3, 3.3, 3.3, because no key was pressed. But if, and here's the concept of keypad scanning. If I hold column 1 here to ground, and if I happen to have a 4 key pressed while I'm doing that, there's my 4 key. So if I connect this to ground and I happen to have this, I check this, it's going to be 3.3 because there's no connection here. But in this case, I've got column 1 to ground, so I've got ground going through here, making a connection because this is pressed all the way out to here, so R2 is going to be ground. This is going to be 3.3, 3.3 because there's no connection. So wherever the row and column is, now if I happen to press, let's say, an A key here, and what I'm going to find is if I connect this to ground, all of these will be at 3 volts. If I connect C2 to ground, these are all going to be at 3.3 volts. If I connect C3 to ground, though, this is going to be at 3.3 on R1. This is going to be at 3.3 on R2, but it's going to be at ground on R3, and it's going to be at 3.3 here. So by pressing any key, the concept of keypad scanning is this. You connect your rows to a pull-up resistor, in our case to 3.3. You connect this one to ground, keeping these ones not connected. So you connect this to ground, and you check to see, is there any key been pressed in this column? No, because all these are 3.3. Then go on to the next one. Connect this one to ground, don't connect these to ground. Check here, is any of these pressed? No, because these are all still at 3.3 volts. Connect this to ground, you check here, whoops, one of them's gone to ground. This row and column intersection is going to tell me which key was pressed, and it should return basically the pattern for an A. Okay, what you're going to find is that for standard keypad layouts, 0, 1, 2, 3, for hex keypads up to C, D, E, F, what you're going to find, each key will generate basically that same pattern. So the 4 generates a 4, a D generates a D, if you have this standard layout. However, not all keypads that have 16 buttons on them are going to have the same layout. And this is our particular hex-like keypad, which is 4 rows by 4 columns. But you'll notice here that the one that's here will not generate a pattern for a 1, it's going to generate a pattern for a 0. So if I pick a 9 here, that's going to generate a 1, 0, 1, 0 because that's in the slot that the A would be. If I take a look at the D that's here, it's going to generate a pattern 1, 1, 1, 1. So when you take a look at standard keypad encoders like a 74C922, it doesn't matter what kind of keypad that you have here, it's going to generate the same equivalent bits coming back or codes coming back for this. So anything like a 7 here will generate a pattern for an 8. And A here will generate a pattern for a 3 based on this. So that's what most keypad encoders will do. Now the situation that we have for our DE1 board for our keypad is we have pull-up resistors to 3.3 volts, not just on our rows, but also on our columns. And what we're going to find is that these 4 pins here, R4, R3, R2, R1, as well as C4, C3, C2, C1, are connected to port A on our microcontroller. Now port A is bidirectional, and we're going to use that concept to be able to decode it, and it's going to take 2 steps. Now here's the concept. Let's just say, for instance, that I want to hit the 6 key. What I'm going to do is I'm going to make all of my row pins here output pins so I can change the voltage. So these are the upper 4 pins. So to do that, if you remember your data direction register, you want the upper 4 bits to be output. You're going to make this F. And the lower 4 pins, these ones here, you're going to make input. So F, 0, and these will be output pins. So the data direction register we're going to make is F0. And as soon as we do that, we're going to put 0, 0 out on port A. Now because these are output pins, this will go to 0, this will go to 0, this will go to 0, this will go to 0. These won't, because these are input pins. So when we put in our zeros here, that means that we got 0 voltage across here, 0 voltage across here, 0 voltage across here, 0 voltage across here. So once we have our value of 0 being driven across these pins here, the next step is to say, okay, let's look at the lower 4 bits, which are now input on port A. And what you're going to find is that at this particular one here, this one here, what we're going to find is that since there's no physical connection between any of these grounds coming across in here, that this pin is going to be at, strangely enough, 3.3 volts. This one here, however, because we've got a ground coming across all 4 of these, but this one is connected here, it's going up through here, down through here. So this is going to be ground, and these other 2 are going to be at 3.3 volts. So we're going to have 1, 0, 1, 1, which is a B. Now what we're going to do is then reverse the whole process, where we're going to make these output pins, so the data direction, and these inputs, so these are the high bits. So we're going to make this for data direction register, we're going to make this 0F. And then what we're going to do is we're going to put 0 on these pins and check these ones. Now in that case, if you remember, that means that this will be 1, 1, 0, 1. So 1, 1, 0, 1 is D, and what did we have here before? B. Now if you take a look down here, this is exactly what we're talking about here. 1, 1, 0, 1, 1, 0, 1, 1, and that means that row 2 is 0, column 3 is 0, and the connection of row 2 and column 3, if we look back here, row 2 and column 3 is indeed the 6 key that we pressed up here. So that's how we're going to do our keypad encoding. Okay, now I've just brought up some default code here, and what we want to do is find out where is port A data. So what we're going to do is we're going to go up here, let's take a look, and we're going to look in our include section. And if we open up includes and look at MC, this guy here, the MC9S08GB32.H, and if we double click on that, and if we happen to be somewhere randomly here, we can hold down Control F to find, and in find we'll put P, has to be capitals, PT, well, let's do that again, sorry, PTAD. So if we do a search for PTAD, then no matter where we are, we can do a find, and there it is. So we've got port A, data register is address 0, and usually fairly close is the data direction register, which happens to be address 3. So that's the information we need. Now what we're going to do is we're going to now go to CodeWarrior in the debug screen, and let's take a look. And what I've done already, let's take a look. You can slide across here, and if you take a look in the left corner, yeah, that's PTAD, port A, data register. And let's go over here, let's go over to address 3 and swipe across here, and if we take a look up in the top left corner, that's PTADD, port A data direction register. Now I've already changed it to 0F, and what I'm going to do is I'm going to put 0, I'm going to, let me turn on my camera here so we can see this. I'm going to hold down the 1 key here with my finger, and at the same time I'm going to put in 00 and hit enter. Notice what I have here. I have E0 because I made this 0F to start. Now that's not the way we want to start. Let's start the way we had in the book. We had F0, and when we hit F0, let's go back and hold down this key again. I'm just going to hold down the 1 key and hit 00 and hit tab. Now when I do that, I get 0E. And if I change this now to be 0F and hit enter and put 00 back in here again, I'm going to get E0. So the two things, E0 and 0E, when you add them, that's EE, which is done in the dummy variable. And if you remember, EE is row 1, column 1. Let's look at the 6 key, because that's one that we really wanted to deal with. So let's go back here that we did in the example, F0. Let's double click on here and make this 00 and hit the tab key. Notice the 0B. And then let's go back here, make this F0 wrong way. Let's go to 0F this time. 0F. And let's put in 00 here again and see what happens when we tab off. We get D. So DB. And that's how we come up with the encoding. Now if we take a look at page 80, it shows us that again row 4 through row 1 are the upper 4 pins, column 4 through column 1 are the lower 4 pins, and here's exactly what we were talking about before. PTADD, port A data direction register, we set to F0 to set all our ports rows so that they can be changed. And then after we've done that, we say PTAD is 00, which puts zeros on our row pins. And what we're doing here is we're using dummy key to read back what port A is. And that's what's going to get that value of 0B. And then when we switch it around, we're going to get adding those two together, doing the reverse thing as we talked about. Then when we add these two together, we're going to end up with DB coming out of this. Now when we go down here, that's part of it. Now the other part is we have to take a look at, well, what are we going to have when we have DB? There's our DB here, and that is the character for a 6. So there's a couple bits of code here that you're going to see. And notice here what we've done is we've made things a little simpler to deal with for our keypad. If this was a standard hex keypad, which it's not, we would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. But for this code to work, we just put in what's in row 1, column 1, row 1, column 2, and so on. We just give her a keyboard layout, and then it says, okay, when you have EE, which is really row 1, column 1, it's going to select our 1. When we have ED, that really means that this is row 1, column 2. That's going to be our 2 key. So this programs that we have here, one of them is going to grab the character, this one's going to interpret it and return it as an ASCII value.